great lunch. So we'll start right away since we want to stay on time for the whole afternoon. So I'm pleased to introduce you Mr. Vicente Núñez Sanchez from the University of Alberta. And the topic of his presentation will be energy balance in gas metal arc welding. Give a good welcome to Mr. Sanchez.
I changed the title just a little bit, but it's mainly about this energy balance in gas metal arc welding. So, I'm Vicente, I'm from Chile, currently doing my master's in the UFA with Professor Mendez, and I'll tell you about the research that I've been doing for this past 2 years. So what's the motivation behind this work? First is to understand, fully understand the theory behind arc welding. In this case, let's go for gas metal arc welding, okay? When we're in this process, we go even narrower to constant voltage and DCEP. That's the focus that we want to really understand. So we want to study the energy on the droplet. What do we mean by that? Is that the droplet temperature. If we can know the droplet temperature, we're sure that we can say some things about it. So if we know that temperature, how this energy in the droplet is going to be, we can say things or we can make improvements regarding with deposition rates or evaporation rates. Okay? So what's the initial analysis that we did? First, we decided to perform some experiments. Some people in the past have done experiments, and they use a solid-state calorimeter, like, this one. Where is it? No, this here. There. So a solid-state calorimeter, where you put a molten droplet on top of it, and then eventually it will cool down, and they both will have the same temperature. Previously, the formula used was this one with some K and some T that were fitted for this purpose. In this case, I decided to go the other way around. I decided to study the cooling rate of this entire calorimeter with the droplet. So here in these graphics, you can see that they both behave in the same way. So we're good. We can move on. So what's this experimental setup that we used? We used a MIG torch here, steady, in this water-cooled cathode, copper cathode, so it has water inside flowing, and we put some thermocouples inside of it, before and after the arc, so the water is going to change temperatures. We're going to know eventually the cathode heat. Okay. Also, it has a hole in the middle where the droplets can fall through into this solid-state calorimeter that is pure copper. Inside of this calorimeter, we have thermocouples where we can see how the temperature increases while we put these droplets. Also, all this is with a data acquisition system so that we can know the different waveforms from this process. And on top of that, we're going to have high-speed videos to analyze the mental transfer of the different droplets. So, the experiments performed were these 5 aluminum alloys: 1100, 4043, 4047, 5183, and 5554. Why these ones? Well, 1100 is pure aluminum, 4043 and 4047, they have different amount of silicon. 5183 and 5554, they have different amounts of magnesium. So we want to see how they evaporate, how they behave. So I'm gonna press play. So we did experiments between 150 and 375 inches per minute. We set them up, and then we changed the voltage in order to have 12.5 millimeters of arc length. So we strike the arc, we move a flux tray, and then we deposit the droplets there that we have the solid-state calorimeter. Okay. So those are all the experiments. So what's the raw data that we obtained from these experiments? First, the droplets. These droplets there, we're gonna have some temperatures. They're gonna look like this. So all the thermocouples that are inside of the calorimeter are gonna heat up and then cool down at the same time, or all together. With this slope, we can know the cooling rate of the calorimeter of the system. So what other value do we need? Or we wanted is the mass of the droplet. Each droplet that was deposited there was taken out very carefully and put it in this balance so that we know precisely how much mass we have there. And then we have the high-speed videos with the different waveforms. Okay, so let's keep moving with this droplet temperature. So with this plot, we can do an energy balance that I told you about. We say initial temperature of the system and then final temperature of the system. And if we move things back and forth, we're gonna end up with this temperature, with this expression. And we can see here this is the temperature of the molten consumable at the initial moment. And then we have here different temperatures. We have the temperature of the calorimeter at the end, temperature of the calorimeter at the beginning. This is the same as before. And then we have these temperatures from the solidus, and no, these are references. Anyway, we have many temperatures that we can obtain from JMAT Pro. Also, the values obtained for the copper, these enthalpies, were obtained from thermocalc, and then we just fitted this equation to it. And that's how we obtained the droplet temperature for this experiment. So let's move on with the results. So for 1100, important thing, we did 3 diameters, or 2 or 3, 1.2 millimeters and 1.6 millimeters, and in some of them 0.9 millimeters to see how it changes. So we can see here 1100 is more or less constant at 2500 Celsius. For the next ones, 4043, we have 3 different diameters. We can see that they're more or less in the same range, the same as 4047. Those are more or less smooth, I would say. But the interesting points are here, the 5554 and 5183, where we, here at the beginning, the 5554, we have these small dips at the transition current. So between globular and spray, we're going to have a decrease of temperatures. And also in the 5183, we see that in the 3 different diameters, okay? So that's a very important point. And here we have some different transfer modes from different electrodes. So we see 4043, this is spray. 5554, as we have this magnesium that is exploding, so almost all the range from the experiments are explosive. And then 1100, that is very smooth and very round globular droplets. Okay. So what we did with these videos is we have this unit model, a model trained with artificial intelligence, and we define 5 different classes. First, the molten electrode, it being orange, the droplet that is going to be in red, external arc, that is the blue one, internal arc, that is the metal vapors, in yellow, and the whirlpool. In this case, I don't have a whirlpool, that's why I don't need to tell this intelligence to learn that. So we took these images, we trained this model, and then this model is telling us many things, many interesting things. So what it can tell us first is the arc length. It's going to tell us exactly, or however we define the arc length, the attachment point. It's going to tell us how the arc is going to change regarding the waveform, for example. Okay, we're going to have the detachment frequency of the droplets. That, well, for a model that we have, we need that value of frequency of detachment. Also, we can get the droplet diameter from each droplet, how they change, and also we can analyze the waveform of all the videos. Okay. So if we move on to our model that we needed these droplet temperatures, we not only needed that value of droplet temperature, we needed the average of voltage and current. Voltage, we set it up, but the current we needed to measure it. So we also need the frequency of detachment, as I told you before. We need the arc length that the model can tell us, and the droplet diameter that also this unit model can tell us. Also, a very important point is the wire composition. By this, we contacted Lincoln, and they gave us the exact composition of each wire. So this model, I'm gonna pass this a bit faster. We define this control volume between the contact tip and the end of the droplet. We also consider there a small boundary layer for evaporation that I'm going to talk a bit more later. And we define heat that comes in minus the heat that goes out, that is going to be different forms, plus the generated is going to be the heat stored in our system. That in this case we're going to say it's 0, okay, because it's going to be in steady state. So, well, if we go into the math and physics, we're gonna define each value of it, and then we're gonna have different heats going in and out. And one of the heats that are gonna get out is this small one, the mass that is going to be evaporating from this control volume. So if we get into that, we're gonna see that this evaporation, there is this one has many different initials and has these small j's. Okay, these small j's means that we're gonna go studying how each element of the alloy is going to evaporate in our system. So all these j's that you can see in those red things are for each element in the alloy, so we can predict how much magnesium is going to evaporate from our aluminum alloy. Okay, so this is a very useful thing to do, and we made it as general as possible so that we can take any alloy, measure the droplet temperature, and then see how much is going to evaporate. And also not just how much, the exact composition. So very useful. And here with our calculations, we consider this mass transfer resistance by each element. We can see that more or less in each element, or at least magnesium, it behaves like 80% is going to be a mass transfer resistance inside the liquid. So a molecule of magnesium moving through the liquid molten droplet inside. Then we have the liquid gas that is going to be this boundary layer that I told you at the beginning. And then we're going to have the vapor that is going to be just magnesium moving through the vapor, through the gas outside. Okay? The main one is the liquid, that is about 80%. But this boundary layer is just a bit less than 10%. So if we want to control things, maybe it's here where we can increase. In the vapor we cannot do much, but in this boundary layer, maybe we can increase it or decrease it, and we're gonna have different effects. So if we look at here, we have the droplet temperature there, and this is the resistance of the liquid in this boundary layer. If we increase somehow this resistance in the boundary layer, we should have a decay in the droplet temperature. So how can we do that? Maybe put some oxygen or some active gas in the mix of gases so that we can create a smaller boundary layer that is going to create a higher evaporation, and then we're going to have less droplet temperature, maybe less evaporation magnesium, or different. So yeah, moving to this evaporation model results, we have here, we can say the exact amount of vapors that are going to have in these alloys. So you cannot tell much about in those graphics. But for example, if we go to 55, 54, we're going to see that magnesium evaporation is going to decrease when we increase the current. And then aluminum is going to increase when we increase the current. Also, we can say by element. So how is going aluminum to evaporate? Well, most of them is going to stay 100% because it's the main component of these alloys. But in other ones, we're going to see that just 20% of the entire composition of the vapors are going to be aluminum, and in the real composition, it's about 90-something% aluminum. So what is the other rest? Well, it can be magnesium in this case. So we see how the magnesium evaporates at the beginning. Almost all of the gases here for 5183, almost all of the gases can be magnesium, which is quite a lot. If we put magnesium on this alloy, we don't want to lose it and throw it into the air. So it's good to see that somehow we are, or we could. So yeah, this model still needs to get validated. I already did the experiments, but need to study them a bit more. So yeah, that's part of the future work that I have to do. First, train this unit model. I still need to segment hundreds of images so that the model can predict better the arc length and the frequencies of the droplet. I have to double check the arc attachment because it varies. The arc, how it attaches to the droplet, If we change the filter for the camera, for example, it's going to change. If we change the current, it's going to change. So we have to double check and define somehow this arc attachment. Then we can also say something about the cathode heat with the different experiments. We should be able to say something. Yeah, maybe we can make some next steps on this evaporation model. We have to still validate it. It's gonna come soon, probably. So I want to acknowledge this to Lincoln Electric. They have been supporting me and giving me the materials for my experiments. Thank you very much.
Does anyone have any questions for the presenter?
It's done the great work, great research work from the direction that was never explored to that level, and so we're all, I think, very excited to see that that research direction, and we're waiting to get more results on that. But I have some questions. We can get one of the previous slides.
Sure.
Yeah, is it possible at some point later down the road to teach your model to recognize compounds, not only certain elements, for example, magnesium oxides? Will it be possible?
I think somehow good. The thing is that the oxide forms after they are like on the atmosphere,
Right.
not in this control volume that we are defining. So maybe if we put some oxygen and we measure it, we can say something about it. But by now we're just working with pure argon. So by now I think it's difficult.
But still great work. Thank you.
Can we go to slide 7? So you're talking about calculating the temperatures using J-meter. The question is, why not you calculate the enthalpies as well from J-meter?
So yeah, all the enthalpy for the copper I obtained from thermocalc, but all the other latent heat and solidus temperature, all those other ones I obtained them from J-meter.
Yeah, but you can get the enthalpies as well from J-meter.
Yeah, but it wasn't as good as we thought. So I compared them with also different sources, and then I decided to just go with this enthalpy for the copper, thermocalc, and all the other ones J-meter.
Very nice presentation, very nice work, but it's very difficult to do all this. Just to understand the procedure, the evaporation rates are calculated right, from thermodynamics,
Yeah, I would say like energy balance, heat transfer equations.
So after you have the temperatures and the properties to calculate the evaporation.
Sorry?
So you are calculating the evaporation rates from the temperature map.
Yes, it's one value that we do need is the droplet temperature.
Yeah.
So yeah, it's like we still need that value. As you can see. So yeah,
It's a bit of a long procedure. That's why I wanted to confirm that I understood.
okay. Yeah.
And do you have any explanation for having a lower evaporation of magnesium at high current? It's very counterintuitive. With higher power, I would expect to have more evaporation. Aluminum evaporates more and magnesium doesn't.
So what I think is happening, and I have to still double check, is that higher currents means more wire fit speed. So it's more material going into this control volume. So probably it's just more material and it's just more aluminum that is evaporating. And we have the same amount of magnesium. Maybe it might be that, but I still have to.
But this is the composition of the gases, right?
Sorry?
This is the composition of the vapor that is coming out of the droplet, right?
Yes. So another thing that can be is that also the shape of the droplet is changing. So
Right,
the surface is.
The ratio of surface to volume might change in that.
Yeah, so that's another thing. Temperatures are increasing, but smaller droplets, they don't have as much time to evaporate as the other ones.
And what the behavior of magnesium and aluminium as liquids when a current is passing through them? I have no idea about this, but I'm just guessing that the magnetic interaction between the materials and the flow of current might not be the same. Perhaps.
Yeah, no, might change. Haven't checked that.
Interesting.
It's a good point. Yeah.
I do have a question. You don't have manganese at all, is that because you don't have manganese in your
Yeah, in the alloys they don't have manganese.
So otherwise you should.
Yeah.
Did you notice a difference in the diameters? The evaporation rates between the two diameters?
So I still haven't been, these are all for 1.2 millimeters. I still haven't not be able to tempt the evaporations in the other diameters because I still don't have trained the model. So it's just throwing me weird numbers, but I have to. The change that I saw is in current, obviously, but yeah, just.
Any more questions for our speaker today? Good. One of them.
Not really a question, but just I think what you've done is how everything will play out different materials, like just regular mild steel.
So this we can also apply this to. We have some previous experiments with clear 80.
I think that the aluminum dissipates heat very rapidly, whereas mild steel is not. So I would imagine the numbers which help.
Yes.
That's all I'm saying.
Yeah, yeah,
It's
no.
interesting to see your study apply to different materials.
Yeah, so we have all values, and this we can see that in this resistance to evaporation, it does change. It is mainly in liquid or steels. So that's all the other two are just zero. So it behaves differently, this evaporation model. So we haven't done experiments. I think we should with other steels. So.
Any other questions for our speaker today? Well, on behalf of the CWB group, I'd like to thank you, present you with a token of our appreciation. If there's no more questions, you guys are more than free to mingle in the reception area. There will be another presentation shortly at 1:30, and it's investigations of defects in map process in the friction stir welding. So I will see you guys in a couple minutes.